recent years, the so-called industrial robot has become a familiar feature of manufacturing plants. This class of machines is, of course, only a part of a much more diverse family of devices characterized by large numbers of degrees of freedom and intelligent controllers. Industrial robots are, however, by far the most numerous, visible, and economically important group of devices in this family. For this reason, much of the material in this chapter is directed at industrial robot design, although an attempt is made to place them in an overall context of intelligent mechanical systems. The manipulator usually has 6 independently actuated joints because a body which moves freely in space has 6 degrees of freedom. Consequently, if the hand of the manipulator is to be placed in an arbitrary position and orientation within the manipulator's reach, then the mechanism must have 6 degrees of freedom. Nevertheless, some industrial robots on the market have as few as 4 or as many as 7 degrees of freedom. Some types of tasks do not require the full 6 degrees of freedom and can be handled by 4 or 5 degrees of freedom style robots. Because the joints usually are not capable of complete rotation but can move only over a restricted angular range, additional degrees of freedom beyond the basic 6 are often useful for demanding manipulative operations. The joints may be actuated electrically, hydraulically, or pneumatically. Each joint is equipped with a position sensor that furnishes the input signal to a servo controller, which positions the joint in response to commands from the central controller. The hand of the manipulator takes a wide variety of forms depending on the operations for which it is being used. Most often, it is a special purpose tool such as a spot welder, a shielded arc electrode, a paint sprayer, or rotary drill. For manipulative or transfer operations, it is often a simple gripper consisting of 2 jaws which close as a vise on the workpiece. The power supply varies considerably with the type of actuation used, but is always present in some form. High-quality servo systems require well-regulated power regardless of the type of system. Hydraulic systems usually have relatively large and complex power supplies because conversion from electric to hydraulic power is performed locally. The central controller is a mini or microcomputer, or more accurately is a set of software resident in that computer which translate a stored program to a series of position commands to the joint servo controllers to repetitiously generate a series of motions. The controller usually includes permanently stored motor and operating system firmware. The latter includes a system for programming the machine and may include capability for writing and reading to tape cassettes or floppy disks. This latter capability permits long-term storage and reuse of programs. It also permits a program generated on one machine to be used on other similar machines. The teach pendant or programming box is used in many robots, particularly those of the so-called point-to-point type. The operator uses controls on the teach pendant to place the robot in a series of positions. These positions are recorded and form the data used by the operating program. Additional programming information may be entered by command buttons or by keyboard entry of instructions. Thus, if the robot gripper is to be moved to a special position and to close at that position during the operating cycle, the operator must move the manipulator using the teach pendant controls until the gripper is in the desired position. Then the operator enters a command to close the gripper by means of the keyboard and pushes a button on each teach pendant, causing the positions of the joints to be recorded. Modes of programming and operating industrial robots vary considerably with the class of function for which each robot is designed. Excerpted Chapter 47, Robots and Smart Machines, by Kenneth J. Waldron, Ph.D., Professor of Mechanical Engineering, The Ohio State University.